Pluto is a far-off and covert, more unassuming planet that was once a piece of our nearby planetary framework. Anyway, progressing upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggested that this cold world is on a potential crash course with Neptune. But how could this truly work? And what may be the consequences of such a tremendous event? Are we seeing a baffling, immense whimsicalness? Or is there another thing to this impending, ceaseless difficulty? Join us as we look at the potential consequences of a Pluto-Neptune influence. Pluto, a previous planet that was renamed as a dwarf planet, remains a subject of interest and study in the vast universe. As shown by ongoing conjectures from leading experts, Pluto's orbit is dangerously close to Neptune's, and astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible disastrous collision between these two planets, which could imply a massive threat to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires a stunning 248 years to complete a single orbit, and since its discovery in 1930, it hasn't even completed one full revolution. However, interest doesn't stop there. Pluto's orbit is marked by its unusually elliptical shape, wandering far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination, which is 17 degrees to the ecliptic plane. The way Pluto follows its path is considerably more erratic compared to other planets. This inclination and irregularity add layers of complexity to its orbital arrangement. Possibly one of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect based on their positions in the solar system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to figure out its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and erratic shape. The mystery grew with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is evidence of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. One more factor for Pluto's situation is this problem, which shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complicated manner. The terms non-simultaneous libration, orbital precession, and VZK wobbling are key to this puzzle, as explained by astrophysicists. What keeps all planets in their orbits is non-simultaneous libration. As for Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is located at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from intersecting. Orbital precession, on the other hand, refers to the upward movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is located far above their orbital plane, adding an extra layer of protection from potential collisions. Another key factor in this situation is the VZK wobbling, named after three scientists, Zell, Kai, and others, who studied how objects move in space. It involves how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pull affects how they move. In Pluto's case, the VZK wobbling helps us understand why its orbit near the Sun is so unusual. Despite Pluto's orbit seeming chaotic, this wobbling helps keep it moving smoothly over extended periods. The VZK wobbling shows that, although things in space appear wild and unpredictable, patterns and laws maintain some control. These forces help keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or veer off course. This three-body problem is essential in understanding how these orbits change because of the way space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and even distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that, despite its stabilizing properties, Pluto's orbit is actually quite irregular, with minor deviations in initial conditions leading to significant differences over centuries. However, these characteristics of Pluto's orbit have been found to maintain stability over long time scales. Monitoring the disturbance from later automatic assessments has helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't alone in this. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit. Saturn also contributes. These studies show that Jupiter's immense gravity is powerful enough to ensure that Pluto stays on a steady path for a long time, possibly even for millions of years. So perhaps Neptune, Jupiter, and Saturn are working together to help Pluto continue moving safely through space without running into trouble. These peculiarities are crucial in keeping everything in place. And in space, without these factors, the solar system as we know it would be a much more hostile place. Bodies like Pluto could crash into others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, particularly, with discussions about it potentially crashing into Neptune in the future, understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can reach a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of constant observation and analysis of these phenomena to better understand our place in the universe. Investigating the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this anomaly. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated. For Pluto's case, this means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using automated simulations has been immensely helpful for researchers in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on one another. By tweaking small details in the simulations, space scientists can see how even tiny changes can have a huge effect on where Pluto ends up. In the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Despite having features like non-simultaneous libration and orbital precession to keep it stable, its orbit can still be inconsistent and irregular. If you start with even a tiny difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. Yet, despite this chaos, Pluto's orbit remains stable over vast time scales, like billions of years. This really means that Pluto's excursion around the Sun has a sort of request to it, despite the fact that it shows up wild at first, anticipating divine developments, especially when they involve sporadic orbits like Pluto's. It is a gigantic challenge. The inherent unconventionality of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future movements of celestial bodies, they also highlight the limits of our predictive abilities. These models heavily rely on the accuracy of initial conditions, and any small mistake or distortion can lead to vastly different outcomes, making exact predictions a daunting task. Other than the chaotic nature of planetary orbits, Pluto helps remind us of the ever-changing and dynamic nature of the universe. While we've made tremendous strides in understanding space, Pluto's case helps remind us of how much our knowledge of the universe still remains limited. Grasping the gravitational impacts of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly influence the stability and course of other bodies within the system. So, why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces trying to keep such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. Tyson's stance on Pluto's renaming is based on the continuously expanding knowledge of our solar system. He views the renaming not as a diminishment, but as a necessary adjustment in line with our growing understanding of the various bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of ongoing learning and change. He sees the complexities of orbits like Pluto's as a sign of how much more there is still to discover in space. The interest in these questions keeps the exploration of space so thrilling. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the fate of Pluto's orbit suggest that we might still have some mysteries to uncover. Will Pluto collide with Neptune, or is this just another moment of confusion in the ever-changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own local solar system. We continue to study these celestial phenomena, determined to uncover more of the secrets that lie beyond. The possibility of a Pluto-Neptune crash raises just another question about the puzzling and captivating universe in which we exist. The potential for a catastrophe between Pluto and Neptune raises fascinating issues about the dynamics of the solar system, as it challenges our conventional understanding of planetary stability. That two celestial bodies with such vastly different characteristics could collide is both unsettling and captivating, especially considering the current relative strength of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be enormous for how we understand gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere primarily made of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is primarily made of hydrogen, helium, and other lighter elements, with a dense, thick atmosphere. A collision between such disparate bodies would dramatically affect their structure and behavior, potentially creating an event that would be detectable across vast cosmic distances. What makes this hypothetical collision especially intriguing is the effect of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in stabilizing Pluto's orbit, it is not the only factor at play. The presence of Jupiter, the massive planet in the solar system, is another crucial element. Jupiter's enormous mass, strong gravitational field, and gravitational influence provide a stabilizing effect on Pluto's orbit, preventing it from wandering too far into Neptune's territory. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. However, despite the apparent safeguards, ongoing research has also shown that the relationship between Pluto and Neptune is not as simple as a direct collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a sort of cosmic lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while crossing in the vast expanse of space, have never resulted in a crash. Despite the determined stability provided by Neptune, Jupiter, and Saturn's gravitational effects, the possibility of a catastrophic collision between Pluto and Neptune remains a topic of great interest among astrophysicists. To truly understand the larger implications of such an event, it is important to delve deeper into the forces at play. One crucial factor in the orbits of both Pluto and Neptune is the concept of orbital resonances. This is where at least 2 orbiting bodies exert regular periodic gravitational influences on one another, maintaining a stable configuration over long periods of time. In the case of Pluto and Neptune, the resonance ensures that while their orbits do cross, The two bodies can never collide because they are locked in a pattern that keeps them at a safe distance. This resonance, often described as a gravitational dance, means that whenever Pluto moves closest to Neptune's orbit, Neptune is always in a position far enough away to avoid any potential crashes. It is a beautiful example of how celestial bodies can maintain harmony in the turbulent environment of space. The significance of this mechanism cannot be overstated, particularly when considering the complex interactions between other planets and moons, especially in the outer solar system, where the distances and gravitational forces are so vast and varied. However, the fate of this delicate balance is not set in stone. The outer solar system is a dynamic place, with the potential for changes to occur over long periods of time. Small, gradual shifts in the positions or velocities of these celestial bodies could eventually disrupt the resonance, potentially leading to unpredictable outcomes. Such a shift could be caused by an external force, such as the gravitational influence of an yet unseen planet or a passing star, or by an internal event, like the gradual decay of the orbits due to tidal forces. Continued observation and study of Pluto, Neptune, and the surrounding bodies in the outer solar system are essential for better understanding the long-term stability of this system. As technology advances and new tools are developed to observe the farthest reaches of our solar system, scientists will be able to refine their models and gain a clearer picture of how these distant objects interact with each other. With new data, we may uncover more about the fragile balance that prevents a collision between Pluto and Neptune, or perhaps discover new forces at play that could alter their relationship entirely.